This is joint work together with Christopher Arnsfeldt Hansen. We have proved it is existential theory of the reals complete to decide whether for a given M player perfect information recursive stochastic game there exists a Nash equilibrium that satisfies some given payoff demands. And this even applies to the case of the game being acyclic with 7 players and the case of subgame perfect Nash equilibria. We have then taken this core result and extended it to analogous problems for the game being deterministic, that is without any chance nodes, the question of a single player being almost surely winning, the mere existence of any Nash equilibria regardless of any payoff demands, and finally also multiple questions regarding omega regular objectives. There has recently been quite a few existential theory of the reals completeness results for multiple types of games. These have though all been games in strategic form or games in extensive form with imperfect information or imperfect recall. To the best of our knowledge, what we present are the first existential theory of the reals completeness results for perfect information stochastic games. An M-player perfect information recursive stochastic game is a directed graph on which play proceeds by moving a pebble from state to state, starting from an initial state. Each state is then controlled by either one of the M players, or it is a chance node, which then has a fixed probability distribution, which then decides what is the next state to move the pebble to. Then a play is an infinite sequence of states through which the pebble has moved. Either this pebble keeps on moving through these states for all eternity, or it ends up reaching a terminal in which it then will loop. If actually a terminal is reached, then all players gain the payoff in said terminal. Otherwise, in the case of no terminal is ever reached and the pebble keeps on moving through states, then all players gain payoff of 0. Then, a strategy for a single player is a conditional plan that specifies where to move the pebble to next in the states she controls, considering the whole history of play up until that point. To ensure decidability, though, of all the problems that we are going to consider later, we are only going to consider strategies that are stationary. That is, they are memoryless in the sense that they do not actually consider the whole history of play, but only the current state the pebble is at. Specifically, we are considering mixed stationary strategies, where the next state is specified by a probability distribution. On the other hand, the strategy could also have been pure, where then there is only given one next state by a deterministic function. And also it could have been positional, where it is both stationary, that was memoryless, and pure, that was deterministic. Then, given a strategy profile with all the strategies chosen by all the M players, we then say that one of the strategies is in a best response to the others if there is no other strategy for said player that will give them a strictly better expected payoff. That is, there is no other strategy for said player with which they will fare better, assuming none of the others will change their strategy. We then say that the whole strategy profile is in a Nash equilibrium if all the strategies in the profile are best responses to each other. The intuition then is that no rational player would have any incentive to change their strategy, assuming none of the others would. For example, consider the following 2-player recursive stochastic game from a thesis of Michael Hummels. First, the first player is allowed to go down and end the game early with no reward for either player, or they may let the game proceed by moving the pebble to the right. Then the second player is allowed to either go down and both players also do not get a positive reward, or she may choose to go to the right and they both get a payoff of 1. This game actually has 2 Nash equilibria. The first one seems very much reasonable. If both players choose to go to the right with probability of 1, then that constitutes a Nash equilibrium. Because if either player would then choose to go downwards with a probability that is non-zero, then they would also just decrease their own payoff, which they would definitely not prefer. But also, it is a Nash equilibrium if both players choose to go downwards with a probability of 1. Because one should notice that none of the players can actually get a positive reward without the help of the other. Yes, sure, the first player might want to go to the right, but the second player has not changed their strategy, so they are still thwarting their attempt. And also, if the second player tried to go to the right, but the first player's strategy is unchanged, then they might want to go to the right, but they're never allowed to try to do so because the first player just leaves the game immediately. Now, the second Nash equilibrium is of course quite undesirable, so we might like to ask whether there exists such a Nash equilibrium which satisfies also some payoff demand, which then puts a lower bound on the payoff for each and every player. We might also ask whether there exists a Nash equilibrium, which is a Nash equilibrium after all histories of play, even the histories that are not in line with the strategies chosen by the players. Because that also fixes the problem we had here. Because the second player would never, in the second state, choose not to go to the right if they actually had the choice and actually got to that state. So the history starting from the initial state and going to the second one, starting from there, the second player would never go down but would always go up. So in that sense, it is not a Nash equilibrium. One Nash equilibrium like this is said to be subgame perfect. With our results, we prove existential theory of the reals completeness for multiple decision problems about these types of games. The existential theory of the reals is the set of all true formulas of inequalities and equalities between integral polynomials with real-valued variables, which are then existentially quantified. This then defines a complexity class as the closure of this problem on the polynomial time many-one reductions. One such complete problem for this complexity class is the decision problem whether there exists a solution to a set of homogeneous quadratic polynomials in n variables with integer coefficients such that the solution itself also forms a probability distribution. If we restrict our attention only to two-player stochastic games with zero-sum objectives, that is, where the players are playing antagonistically against each other with simple win-loss payoffs, then the complexity of the decision problems stay relatively benign. For in that case, one can reason about the so-called value of the game, which is the best possible expected payoff a player can get against the strongest response the opponent can have to counter it. We say then that a strategy is optimal if it ensures the value of the game against all strategies of the opponent. In recursive stochastic games, both players have optimal positional strategies. And a content has shown that deciding whether the value of such a two-player zero-sum game is above some given threshold is both in NP and also in co-NP. Whether this actually is solvable in deterministic polynomial time, that is still an important open question to be answered. One can solve this in deterministic polynomial time if said game is deterministic, that is, without any chance nodes, or it only has a single player controlling all player controllable states. This setting of two-player zero-sum games are very much a traditional setup for the field of verification, because they're very good at encapsulating the idea of the controller of a system that is defending itself against an adversarial environment. But in many of these cases, they don't use merely just the terminal to actually determine whether there is a win or loss, while the payoff is Borel, where all the states in the entire, possibly infinite, history of play actually contribute to whether a player wins or loses. But in even those cases, still, quite a few times, such as for parity games, players still always have at their disposal optimal positional strategies. But when we go to games with more players or with non-zero-sum objectives, then things get more complex. The primary problem we want to consider is deciding the existence of a Nash equilibrium that satisfies a given payoff demand for a given in-player perfect information recursive stochastic game. This has already been investigated back in 2011 by Hummels and Botchak. Back then, they showed that it is NP hard already for 2 players and non-negative rewards. They've also shown NP hardness for deterministic n-player games, where deterministic again is without any chance nodes, and here then also n is part of the input. They also proved square root sum hardness for 4-player recursive games with non-negative terminal rewards. Here, square root sum is a problem that is exemplary for the difficulty of computing with real-valued numbers. In the case of deterministic recursive games, Hummels and Botchak also showed square root sum hardness for 8 or more players. They also have already shown membership in the existential theory of the reals. They wanted to prove p-space membership, but they did so by showing existential theory of the reals membership as it is contained within p-space. What we do is provide a hardness result for the existential theory of the reals, and with that, fully settling the problem's complexity. We do so by a polynomial time many-one reduction from the complete problem of homogeneous quadratic polynomials I mentioned earlier. That is, given an instance of homogeneous quadratic polynomials in n variables with integer coefficients, we have to construct a recursive stochastic game and a payoff demand for it, such that there exists a Nash equilibrium that satisfies the payoff demand if and only if there exists a solution to the original set of polynomials. We construct this game by use of multiple gadgets, 2 of which we want to present in a little more detail. The first of the 2 is one where player 1 will assign values to the n variables x1 up to xn. We will then later copy these values into the other gadgets. In this gadget, a chance node leads with uniform probability to n nodes, each then representing a single variable. At node vi, player 1 may then either choose to give payoff to player 2 and 4 or to player 3 and 5. In both cases, player 1 will gain nothing. We can then interpret the expected payoff of player 2 as the value of the variable xi and the expected payoff of player 3 as 1 minus xi. Back at the chance node, the expected payoff of player 2 is then an nth of the sum of all of these payoffs. So if she expects at least an nth in the payoff, then their sum is at least 1. Similarly, if player 3 can expect at least a payoff of n minus 1 over n, then their sum is at most 1. This means that with payoff demands on player 2 and 3, we can force the assignment of player 1 to resemble a probability distribution. We can then copy these choices of player 1, these values, into other gadgets by use of threads. Because consider this little game. At first, player 2 and 3 may threaten to go downwards to the node vi from the prior gadget. If they do not make use of this threat, then player 1 may choose to either give payoff of 1 to player 3 and herself, or proceed into a subgame where both player 1 and 2 always get a payoff of 1. Consider then in this game a Nash equilibrium where player 1 can expect a payoff of 1. Then player 2 and 3 have not made use of their threats, since player 1 did not gain anything in the prior gadget. Here then both players put a lower and an upper bound on the choice of player 1 at W3. This node then must behave similarly to vi. We can then repeat the same idea, but now with independent threads for player 4 and 5 to then achieve multiplication of the variables xi and xj. Because here, if player 1 can expect a payoff of 1 in a Nash equilibrium, then player 2 and 3 ensured that we reached the threads of player 4 and 5 with probability xi. At the same time, player 4 and 5 enforced that we only get to the upper right terminal with probability xj. Counting it all from the beginning, this is exactly the probability of xi multiplied with xj. So, we can introduce a 6th player to get a constant alpha multiplied by the product of these probabilities in her payoff. We do so by giving her set constant alpha in this very terminal and nothing everywhere else. The rest of the construction then repeats these same ideas. to simulate a single polynomial, we use chance nodes to sum the values within the probabilities together. That the polynomials then are equal to 0 can be checked via threats for the 6th player to enforce a lower bound, and we can add a 7th player to also enforce an upper bound. Finally, all gadgets are combined into a single game with even more chance nodes. On the full construction, we can then place payoff demands on player 1 to ensure that there are no threats that are used, and on player 2 and 3 to ensure that player 1's assignment actually resembles a probability distribution. And this then constitutes the full reduction, because there's only going to be a Nash equilibrium that satisfies this payoff demand if and only if there exists a solution to the original set of homogeneous quadratic polynomials. We also notice about this construction that it is acyclic and it only uses a constant of 7 players. Furthermore, we also notice that this Nash equilibrium that may exist is actually subgame perfect, so we can also extend our result to that analogous problem. Then, using this co-reduction, we can extend it to many analogous completeness results. First of all, we will notice that since the game is acyclic, we can always guarantee that all plays end in a terminal. This allows us to use a modified version of a gadget of Hummels and Botschak to then replace all the chance nodes in the prior reduction. The gadget is designed with payoffs such that in a Nash equilibrium, 2 players force by threats a 3rd player to leave from the gadget with a similar probability distribution as was in the original chance node. We will notice in the original construction that most of the chance nodes we had were actually completely independent of each other. So we can actually reuse the same 3 players to implement most of them. With only 6 more players then, on top of the original 7, we can then extend our completeness results to the analogous problem for deterministic games. We still also keep subgame perfectness, so we also extend our results to the analogous problem of subgame perfect Nash equilibria in deterministic games. By use of threats, we can also simulate the payoff demand from the earlier proof. With this, we obtain a similar result for the case of a single player being almost surely winning. We do so by only adding 1 extra player who wins if none of the new threats are used and instead a terminal in the original construction is reached. Still, in this case, we also keep the analogous result for subgame perfect Nash equilibria. Recently, there has been constructed quite a few gadgets that actually do not allow any Nash equilibria to exist within them. If we allow our players to threaten to go into one of these rather than going into our main construction, then we can extend our results to the mere existence of any Nash equilibria, regardless of any payoff demands. We do though, with this, lose the analogous result for subgame perfect Nash equilibria. Because if there is a Nash equilibrium for the full game, it's still not going to be a Nash equilibrium from within that gadget, and there is a history that leads into the gadget. In a similar way, we also extend our results to multiple budget objectives, such as stay in a set games with safety objectives and reach a set games with reachability objectives. Throughout this whole presentation, we will notice we have only been looking at recursive stochastic games up until this point, where players only get their payoff at the terminals. One could think of a much more general setting where players are allowed to accumulate their payoff throughout the entire, infinitely long history of play. One such more general setting is mean-payoff games. Here, each transition between states has some value, and the payoff to a player is the limit of the mean of all of these infinitely many values visited. We notice that all our terminal rewards are non-negative fractional rewards between 0 and 1. Hummels and Botschak have noted that one can translate these into cycles with binary rewards of a mean-payoff game. So, if all of the transitions have their values set to 0, then we obtain completeness results for mean-payoff games with only binary rewards. And this even applies to the case of the game being deterministic and or the case of subgame perfect Nash Equilibria. If we look at more general types of strategies than only stationary, memoryless strategies, then Hummels and Wojcik and others have already shown it to be undecidable to check the existence of a Nash equilibrium that satisfies some payoff constraints. But if the game is acyclic, then it is decidable, because one can unfold the acyclic game into a game tree, and at that point each state already encodes the entire history of play up until that point. So in that case, all strategies are stationary. We find it still an interesting problem for further investigation to find the exact complexity of more general types of Nash equilibria that satisfy some payoff demands for acyclic games. Thank you for watching. For a more technical description, we would like to refer to the paper.